Okay, all right. So, well, happy week 8 Monday, everybody. It's kind of crazy that it's week 8 already, and we just have a couple. We have this week and 2 more weeks, and then it's finals, and then it's spring break. So, so it goes by quickly, right? Any do we have like any transfers from like community college where they were on semester system? No? Okay, everybody. Well, how do you like the change of pace, right? So, anyway, I always grew up on the quarter system, and I've grown to love it, or I enjoy it. I enjoy the quick pace. I feel like we can cover a whole lot this way. I know it's a little bit. Yeah. Okay. Anyway, so on Friday we covered. We started talking about unidimensional optimization, and we said, well, so far we have a bunch of root finding methods. Let's just take the root finding method, which says it's going to solve for where the equation is equal to 0. Let's take that and apply it to a derivative, right? So we said all we have to do is, if there's some function that we want to optimize g of x, take the derivative of g, we'll call that f, and then we use a root finding method on f, okay? And if we find where f, or where the derivative is equal to 0, then that will give us the critical points of g, okay? And if we have the critical points of g, then those should either be local mins, local max, maybe they're saddle points, things like that, but this is where we left off, okay? And we said, all right, well, let's just kind of take a look at how this works for something like Newton-Raphson. And so for Newton-Raphson, we just said there's some function g of x that we want to optimize. We're going to let f of x be g prime and f prime be g double prime. And so up here is Newton-Raphson for finding the root of f of x, okay? And that, if we just change everything to g prime and g double prime, then it will be for finding critical points of g of x, which should correspond to local mins and local maxes, or saddle points and things like that, right? Okay, is that so far so good? We're just going to use the same root finding method that we had before, but then we're going to apply it to a derivative, find where the derivative is equal to 0. Okay. So an objection that came up was, I thought the whole point was to avoid math. What if we don't know how to take the derivative? Okay, valid objection, okay? Today I'll show kind of just a trick that we can do. Again, we're doing numeric methods where all we can do is just plug in values and get values back, right? So we're going to say, well, let's plug in some values and see if we can use that to get our get a derivative here, okay? And so conceptually, what is the definition of a derivative? Okay, but all right, so it's a limit, right? Conceptual definition of derivative. And it was the limit as what? What went to what of what and what?
Delta x.
Yeah, so it was the limit as, we'll say delta goes to 0. And what was in the numerator, right? So if we wanted g prime of x, okay, this would be g of x plus delta minus g of x divided by delta, okay? All right, so this, we're going to use this in a numeric way to estimate derivatives, okay? And so basically, what I'm going to do is we're going to say we have some function, I don't know, that looks like this, okay? And let's say we are right here. This is going to be our, I'll call this x0 or whatever. And what I'm going to do is I'm going to just add a tiny, this will be x plus delta, okay? And to kind of avoid any kind of bias that we may get from having this, I'm also going to go to, I guess, x0 minus delta, okay? And I'm going to calculate this point, and I'm going to calculate this point, and we'll take the difference, all right? So up here I've got f of x0 plus delta, and down here I've got f of x0 minus delta. And then so we'll get an approximation will be equal to f of x plus a delta minus f of x minus delta, okay? And what is the width that we need to divide by? 2 delta, okay? And this allows us to approximate the derivative without having to do any kind of calculus, okay? So we don't have to do any kind of math. We can just ask the computer, figure this out, and this will give us a pretty good approximation for the derivative. Now, we often just choose a small delta, okay? Maybe delta can be something like 1 times 10 to the negative 5 or something like that. But of course, I don't know if this is an of course, but depending on where you are in your function, you can, maybe you want to use an even smaller delta, or this delta might be, it might produce values that are too small to register on the floating point system, right? So if you're dealing in the realms where x is like trillions or something like that, plus or minus 10 to the negative 5 might cause some rounding issues where they end up being seen as the same value in the computer. But anyway, so I've coded this up, and let me just kind of demo numeric derivative, okay? So this will be an approximation, but pretty good, okay? So this is numeric approach, numeric approximation of the derivative. Oops, okay, hang on. Something's going crazy here. Oh wait, that's the other thing. Okay, so are you guys able to see this? Okay, so we're going to start off. I have this function, 0.25x to the 4 minus 0.5x squared, okay? So this is going to be basically the function, what do I call it, g? Okay, so g of x is basically 1/4 x to the 4th minus, what is that? 1/2 x squared. All right, and I picked these with these coefficients so that they cancel easily when we take derivatives and stuff like that. Okay, so anyway, when you, so this is our function g, and we say, all right, let's find g of x, and we'll plot this, and this is what it looks like, okay? All right, let me actually, let's just copy this plot. Okay, copy to clipboard. Copy plot, that's good. Let's throw this in here. Here's our function. Okay, great. And so let's say we want to like find a local min or max, right? So we're going to try to optimize these. So we've got 3 locations, -1, 0, and 1, things like that. This is just the x-axis for us, okay? All right, so anyway, here is the derivative. It's a function. And what this function will take in as arguments is going to be some function that we've written out, ftn. It's going to take in an x and then a delta, okay? And I have default value of 1e minus 5, but you can change that to whatever you want, okay? And then so I've got x on the left will be x minus delta, x on the right will be x plus delta, and then the derivative will just be the function of x on the right minus function of x on the left divided by 2 times delta. Okay, so that's exactly what we discussed, and we'll try this out. Okay, so so now using the derivative, I'm going to create a new function. Well, I don't. Here, let me just kind of show how this would work. Okay, so if I say let's find the derivative. Let's find the derivative of g of x at 0, which will be, or let's do derivative g of x at 1. Okay, so we'll say derivative of g at 0. Okay, and when I ask for that, it gives me back 0. Right, and then and I can ask, well, what's the derivative at g equals 1.5? Okay. And it tells me that the derivative should be 1.875 or something like that. Okay, and we can actually compare, because we can do the calculus, and the derivative of this, like from calculus, we know that g prime of x is going to be x cubed minus x squared, right? And so I could say, well, what's g prime of
minus x?
What?
Not x squared.
Oh, minus, yeah, thank you. Okay. All right, and then okay, and then so this will be 1.5 cubed minus 1.5, and if I do that, you know, 1.5 cubed minus 1.5 gives me 1.875. So my thing's giving pretty good values here. Okay. So anyway, instead of just going through and calculating the derivative of g of x for everything, I'm just going to create a new function called numeric g prime. Okay. And this is going to be the function of x of the derivative, and it's all this is doing is it's just plugging in x into the function derivative g x, okay? And so it's going to return that value, all right? Oops, and I need to call this numeric g prime. So I'm going to do that, and we calculate numeric g prime, and then I'm going to calculate the derivative, okay? So this is the derivative of the original function there, okay? And so just to compare the results of my numeric derivative, where I'm just taking each value and adding delta, subtracting delta, and dividing that difference by 2 delta, I'll use the actual calculus formula, x cubed minus x, okay? And I'm going to call this actual g prime, okay? Actually, I need actual g prime. Okay, so we're going to have actual g prime, and we're going to calculate actual g prime of x. And then I'm going to graph this using a green line, a green dotted line. Okay, and when we do that, it's like exactly on top of each other. Okay, so our numeric approximation is pretty good. Okay, and in fact, you can ask if everything is equal. So there's a function. So if I say, you know, what is numeric g prime of x? What's the first value? And what's the actual g prime of x? Okay, well, if I do options digits equals 17 or something like that, okay. Oh, wait, that's actual, and I need the numeric, okay? So we can see that the actual and the numeric derivatives are slightly different, okay, if we extend all of these things. But there's a function called all equal, all right? And all equal, if I ask for the help, it basically asks, are these two things nearly equal, okay? And it basically says, well, you know what, we're dealing in floating point, so we know that if we take everything out to like 17 digits or whatever, they're not going to be the same. But are they the same up to like 8 digits, 9 digits, or something like that? And then, and so it has a default value, I think, of a certain tolerance, which is 1.5 to the times 10 to the negative 8. And if it's within that, it's going to say yes. All right. So if I say, are these two things all equal within this tolerance, it returns back true. Okay. So that's a good sign, right? So we've got this thing. So I'm going to go ahead and copy this to the clipboard and put this in here. And we'll say, okay, so the blue is numeric derivative. Is our numeric approximation. And then the green is the actual derivative. Okay, at least within as accurate as floating point can give us. Okay, all right. So so that's good. And then the thing about this derivative function is you can just keep applying it, right? So I called g prime. Numeric g prime is the derivative applied to g, and I can say, all right, let's call this double g prime, and I'm going to apply it to the numeric g prime function. So the numeric g prime itself is a function, and I can apply the derivative function to that, and we'll call this g double prime. Okay, this should be f double prime. Sorry. Okay, and then so I'll do that, and we can graph g double prime. And as expected, the derivative of a cubic function looks quadratic, okay? And all we're doing is we're just taking the derivative and applying it to the numeric g prime function. And then the actual double prime, maybe I'll call this actual double prime, using calculus is going to be 3x squared minus 1. So I'll call this actual double prime. And we'll do that. And then again, I will graph this using a dotted line, okay? And again, using the actual thing, we see it line up pretty much exactly on there. And then so let's compare g double prime of x versus f p dx. Okay, the g double prime versus the actual double prime values. Okay. Oops. F dpx. Thank you. Okay. And so here it says, well, it's not true in that they are all equal, but it says the mean relative difference is 7.3 times 10 to the negative 8. Okay? Meaning that the computer detects that they are not exactly equal. Okay? It says the values have drifted apart a little bit, but that mean relative error is on the order of 10 to the minus 8, okay? Which I would say for us, I don't mind this kind of difference here, okay? So it's probably good enough, okay? And so anyway, so that works, and I just kind of wanted to show you just like another example here. Here I've got this is the sine function. And if I apply the derivative to the sine function and I graph that, it looks like the cosine function, okay? And if I compare that to the actual cosine function, we can see that those values line up exactly on top of each other, okay? So even if we can't do calculus, all right, we've got kind of these little numeric tricks up our sleeve that that we can use to get approximate derivatives that, if we're trying to prove some kind of mathematical theorem, this is probably not the way to go. But if we just need approximate answers, which is generally anytime you're using a computer, you've already acknowledged that you're just going to get approximate answers. It's pretty good. Okay, so now we have the red is going to be the g double prime of x numeric approximate. And then the green is the actual. Okay, so so even so all of these methods that we learned earlier, all of these root finding methods, I said, oh, they can become optimization methods if you apply it to the derivative. And we said, well, what if I don't know how to take the derivative? Okay, we say, well, you can approximate the derivative, and that's probably good enough. Okay, so anyway, that's pretty good, right? All right, so so we have all of that, and then we have another optimization method. And so, you know, all of these methods that we had earlier, they will fail if the root finding method fails, right? So if the root finding method fails, like Newton-Raphson fails in the root finding thing, then it's not going to work for the optimization either. We do have a method for optimization that works, and this is called the golden section search. Okay, I have linked to a video in your homework from somewhere in your homework. There's a link to a golden section search video. Okay, make sure you watch that. All right, it's a very good video. I'll show you some stuff in class, but I feel like everything that was covered in the everything I'm going to show you here is probably covered in the video, probably even better than what I'm doing here. But anyway, watch that video. I think it's really good. I will show you how it might work here. Okay, so no. Okay, so what I'm going to do is I'm going to take this same this function that we drew earlier. Okay. And I'm going to zoom in on 0 to 1.5, okay? And we are going to just optimize this portion of the of the function, okay? Which means we're looking for this minimum right here, okay? We're going to look for this minimum right here, which is at 1, okay? Which we can see if I plug in, you know, 1 here, then that's going to work. Okay, so anyway, I take the function, and I'm going to go from the lower bound, which is going to be 0, to the upper bound of 1.5, create a sequence, and I'm going to draw this plot. Okay, so this is just that portion of the thing, and we want to optimize it, and we want to find this minimum. Okay, do you guys remember what the golden ratio is? Okay, well, yeah, it's right here, but the idea of the golden ratio is so here's a square, and here is, I don't know if my picture's no good here. I probably need to do a little bit more here. Okay, so the idea here is you've got this rectangle. Okay, so we're going to say the sides of this square is 1, and this side is going to be x, okay? And the ratio between this edge and this edge is going to be equal to the ratio between this edge and this edge, okay, of this rectangle. So if you take the big rectangle and then you just shrink it, they end up being the same. So you're going to get the ratio of 1 divided by 1 plus x is equal to the ratio between x and 1. Okay? And then so you can solve for x, and basically you get, I forget what it turns out to be, but basically something around 1.618 and 0.618. Okay? And so what happens is if you do 1 divided by 1.618, it's equivalent to basically 0.618. It's 0.618 over 1, okay? Which is pretty pretty neat, right? Okay, so that's what the golden ratio turns out to be. So it turns out to be this thing, golden dot ratio, yeah, 0.6180339. Okay, and there's a reason why we do this, all right? And it's not like, oh, this is a pretty number and we use it for the Fibonacci sequences and throw it on top of random images and say, wow, math is amazing. Okay, but anyway, so we've got our lower bound, 0, and our upper bound, 1.5. And so what I'm going to do is I'm going to take this difference of 0 to 1.5, multiply that by the golden ratio, and add that to 0. Okay, and that's going to be x1. And then we take the upper bound and we subtract off the golden ratio, and we have that. And so our 2 points end up kind of 60, about 62% of the way from 0 to 1.5 is right here, and 62% of the way from 1.5 to 0 is right here. Okay, so let me just kind of copy this image. So here's the thing that we want to, okay, so going from here to here, this has a distance of 1.5, and then going from here to this spot is going to be 1.5 times the golden ratio gets this symbol phi for whatever reason, and then coming from here to this spot is going to be 1.5 times phi as well. Okay. So those are our two locations, right there and there, and we call this boundary x1 and this one x2. Okay, it's a little bit. I know it's a little bit confusing to have x1 on the right and x2 on the left, but that's just how I think the Boulder, Colorado video does it, and so just to avoid confusion, I'm going to follow the same thing here. Okay, so we've got x1 over there and x2 over here. So what we have is we start off saying we know there is a minimum value, or at least a local minimum value between 0 and 1. I'm sorry, between 0 and 1.5. Okay, and then we took two kind of test points here. Okay, I'll go ahead and make these. We've got this location and this location. All right, and what we have is that the function at x2 and the function at x1. So we say, all right, there has to be a minimum between 0 and 1.5, okay? And I'm calculating the value at x2, the function at x2, and the function at x1, okay? So, what I can say is that I can safely be sure that the minimum is not going to be over to the left of f of x2. Why? Because if it were, then f of x1 would not be lower than f of x2, okay? Because the fact that the value to the right of f of x2 is lower than the value of f of x2, so the fact that f of x1 is lower means that the minimum value has to be between here, between x2 and 1.5. Okay, I can safely eliminate this, and we know that the local min is not going to be over there. Okay, so because f of x1 is less than f of x2, we know that that the local min is between f of x2 and 1.5. Okay. All right, and so what we do now is that this thing will become our new left bound. This will maintain as our right bound. Okay, and we're going to apply golden section search on going from the left to the right. Okay, so now we iterate. And we repeat the process. Okay. So some of you might think, well, in the next iteration, what we've done is we're working with a zone that's about 38% smaller because our golden ratio is about 62%-ish. Okay. So you might say, well, why don't I just like take two values really close to the middle, like 49% of the way and like 51% of the way, and then I can compare those two, and then I can say, well, because this one's lower, I can still kind of make the same process of elimination. And we would be a little bit more efficient in that we would only have like, we would get rid of like 49% at the time. That is true, that would work, that's a perfectly valid method. But the reason why we like golden section search is because of this magical property of the golden ratio, in that when I repeat this process, I can actually reuse this value. This value, which was 62% of the way from 0 to 1.5, is actually now 62% of the way between our new left and right bounds. Okay? So this value of x1, because of the property of the golden ratio, this becomes my new x2, and it is from the right minus left times phi. Okay, so I don't have to actually recalculate a new point, and I don't have to actually recalculate f of x2. And that might not seem like a big deal, okay? Because you're just like, who cares? You're saving one calculation. I thought computers can do calculations cheaply. That's true, sometimes, okay? Sometimes calculating this function f is like, maybe your function is really, really, really complicated, and it takes a lot of computational power just to calculate this thing, okay? You can imagine a time where, I don't know, every time you wanted to ask, what is the value of the function at this location? It costs you $1, okay? And in that case, you don't want to, you want to like get the most out of each time you bother calculating this function. So, so being able to reuse these function values is very handy for us, okay? All right, so anyway, we do this, and I went through all of this trouble here. So I said, we're going to calculate the value of the function at x1 and x2, and I'll put these points here, so that here you can't really see these. Maybe I should make them, is there a dark green? Maybe. Okay. It's like, it looks just black, but all right, dark green it is. Maybe I'll say like size equals 3, just for emphasis. No, I guess size? Maybe size is not a graphical parameter? What is it? For points? Point size scale. No, okay, never mind. Getting my ggplot mixed up with my base graphics. So, all right, this is just life. And what we have is something broke. Okay. F2 is greater than F1. All right, so again, we're going to set this to be our new lower bound, and I'm going to replot this. So this will go from around 0.6-ish to 1.5, okay? And so when I plot this again, it looks like that. So going from around 0.6-ish to 1.5, we have that. And I can just take what used to be x1 and f of x1 without doing any actual recalculations. Here, maybe I'll just kind of demonstrate this AB line at our x2, okay? So this is what we used to have, and so this line that was right here at 0.9-ish ends up being this line right here, okay? At the same, you can kind of see if you just focus on the green line, which is about 32% of the way, or 38% of the way over, you could see that its relative location on the scale is exactly the same, right? It hasn't moved, and that's because of the golden ratio. So I haven't done any recalculations. I just reassigned x1 to be x2 and f1 to f2. So this is just reassignment. And now I have to say, all right, let's figure out what this spot would be, okay? What that right line would be, and I have to do that. And so that's going to be lower plus the golden ratio, and we have to calculate a new f of x1, and we can calculate the new AB line. Okay, so these spots end up being the same. Okay, I mean in relative locations, and then we're going to calculate these 2 points. Right. Okay, and so this time the right point f1 is larger than the left point. Okay, and because we know a local min has to exist between the two endpoints, the fact that this is larger than this point means that the minimum has to be between over here and here, okay? And I can safely eliminate this side now. So let me just go ahead and copy that. We'll copy this plot. So we're zooming in. Okay, and then we calculated. Again, we calculated this location right here. So this is our new x1. So this is I'm sorry, this is our new x2. Okay. Okay, and this is a new calculation. And then because this spot is lower than this spot, we can eliminate this side. All right. And we know the minimum has to be between 0.6 and 1.1-ish, okay? Something around there. And then we just keep repeating this over and over and over again, okay? So we just, so this will become our new bound, and then I will zoom in on this portion here, and we calculate our new locations, so on and so forth, and then we just keep kind of shrinking down our so I'm just continuing to zoom in on these spots here. All right. So so this. So x1 equals the new right upper bound. The lower is still the lower. And then this x2 becomes x1, and then we'll have to recalculate. I'm sorry. I have this wrong. This location becomes this location here. Okay. So yeah, x2 becomes the new x1. And then we'll have to calculate a new thing, and we continue on, and then we can eliminate this. And you'll just keep zooming in, and it will continue to iterate. Okay. I think I have the code written up as a while loop and it's included already in your homework, and you use that for the coordinate descent. Okay, so you use and I mean any of the unidimensional optimizations thing can be used for coordinate descent, and we'll talk about coordinate descent I guess on Wednesday there. Okay, but here's just kind of a numeric method for continuing to zoom in on all of this stuff here. Okay, so you're starting off with some kind of function. You calculate these two locations according to the golden ratio, and each time you can eliminate kind of one of these panels, and shrink in on and zoom in further and further on a certain location. And the nice thing about the golden ratio is that it allows you to just reuse a value rather than having to calculate two new locations every time. You only have to calculate one new location each time. And so that's golden section search. And with that, we'll end today's lecture, and we'll see you guys on Wednesday.